Hi everyone, thank you so much for joining us in this second masterclass here at 42 Lisboa. As you know, these masterclasses are powered by Women in Tech, thanks to Carolina Natal, who is going to come give you a word in a second. And we are really thankful for this initiative, because for us it's really important to bring other topics that can better this experience at 42, and we are really happy that you join. And today we are going to be talking about nanotechnology. So thank you, Diana Gaspar, for joining us, and be sure to check the other ones as well. We are still running for some weeks until the end of November, so I hope to see you all here in those sessions as well. Welcome, Carolina Natal. Thank you.
Hey everybody, good to see you again today. I hope you enjoy it like you enjoyed last week. A bit the reason of why this masterclass started, I did exactly the opposite way, which was I started in nanotech and now I work in IT, and the idea is to bring to IT a little bit of nanotech. So today we're going to deep dive a little bit into the concepts and what is nanotechnology. Last week we talked about microelectronics, and in the next weeks we're going to talk about AI, we're going to talk about quantum computing, cybersecurity, and how these technologies get it together and influence entrepreneurship or even the cybersecurity field. So I hope you enjoy. I made a joke last week, which was, by the end of these master classes, I want to see everybody coding in assembly. So maybe this will motivate you for it. And I hope you enjoy, and this sparks a little bit the curiosity on these fields. So to the stage, I would like to invite Diana Gaspar, which was a professor for me in uni. And I'm very happy to have you here today. And go for it.
Thank you. So good afternoon, and thank you for staying around for this, let's hope, interested masterclass. And today I will speak to you a bit about nanotechnology. Just give you a glance, because nanotechnology is way broader than what I will speak about. But just to frame you, nanotechnology, or at least the first idea of nanotechnology, was just presented in the late 50s from last century. Richard Feynman, in a talk, he gave a talk speaking about with a very interesting name, "There is plenty room at the bottom." What he meant with this means that at nanoscale, or a very atomic and molecular scale, for him, he stated that, okay, you can speculate that you will be able to manipulate atoms and make what we call tiny machines. Okay, in this, when you Google for nanotechnology, immediately Richard Feynman came as a result of nanotechnology. But in fact, only in '74, the nanotechnology concept was presented by Norio Taniguchi. He coined the nanotechnology term, saying that it mainly consists of a processing, separation, consolidation, and deformation of materials by one atom or one molecule. Since then, it was a huge breakthrough, but nothing was done until the 80s. Why? And last week we spoke about the problem with nanoscale is the tools and the characterization equipment to make it visible, to make it happen. So, in fact, the nanotechnology only came up or arose 40 years ago, less than that. So, all of us, we heard about nanotechnology or nano, but how big is nano? Maybe it's, or at least for myself, for me it's very difficult to relate with this scale. I can say that a nano is 1/billionth of a meter. Okay, it's 10 to the power of minus 9 of the meter. Okay, you say it's a number, but let's go and see how small or how big actually it is nano. If you have a guitar, which is typically 1 meter, and divided by 100, you will have like a blueberry size, 1 centimeter. And if you divide it again by 10, you will have eye of a needle, 1 millimeter. And then, if you divide it again by 10, you will have like a thickness of the piece of paper. Still, it's 100 microns, way above 1 nanometer. And again, if you divide by 10, you will have a red blood cell, more or less 10 microns. Divide again by 10, and you have a bacteria. It's quite small already, but it's 1 micron. And just to let you know, this, more or less, this range, it's perceptible to the human eye, okay? You can see your hair, it's more or less half of this thickness, but below this thickness start to be very difficult to see. But then, if you divide again by 10, resuming the bacteria, we will have the average size of the coronavirus, still 100 nanometers. And then divide again by 10, we will have 10 nanometers. And in fact, 10 nanometers, if you put more or less 20 atoms of silicon, it's 10 nanometers. So if you want to go even further, we are speaking just a few atoms to make 1 nanometer. So this is how big a nanometer is. And if you want to make it more close to our reality, if you put a marble as a nanometer size, our planet will have 1 meter in comparison. Or if every person on Earth, if all of us measure 1 nanometer, a single Hot Wheels car will be enough to put it all the population, worldwide population, on that very small vehicle. So it's very, very, very thin. So we are speaking in a totally different scale, different from what we perceive from our real life, let's say. So means that eventually different scales, same rules, or maybe not. Let's find out. So to start deep diving a bit on this, so I want to ask you, and please feel free to interact. I want to ask you, what color is the gold? Any thoughts? Yellow. Yellowish. Yes, at micro scale. But then, if you go to the nanoscale, do you think the same happens? So, in fact, gold can be red. So, depending the size of the nanoparticles, from, for instance, one particle of 20 nanometers will be very red, while a bigger one will be more for the pinkish or purple. But in fact, it can be even more different. Gold can be blue, can be green, depending on not only the size, but also the shape. So that's why everything at nanoscale, or all the rules that we know for the macro scale, maybe you cannot think as the same for the nanoscale. But in fact, we think that nanotechnology, let's say, it's very trendy, it's something very, very new. But if you go for instance, this is one of the first examples of nanotechnology, is a chalice from Romans, and they used a mixture of gold nanoparticles and silver nanoparticles. And you see, in this case, the cup or the chalice looks green when you illuminate, you shine the light to the chalice. So it means that the green light will be reflected. And in fact, if you shine through the glass, the glass will become red. Why? Because maybe they don't know at that time that they were using nanotechnology, but in fact, when they produce this, they use gold and silver nanoparticles, colloidal mixtures, and they put it together on the molten glass. And then they form the glass without knowing, or maybe they don't. We don't know. We don't have the scripts stating that they were using this with that knowledge. And we can have these two very different colorations depending on the illumination. But in fact, all of us in Portugal, we have a lot of churches and other buildings from the medieval era. And in fact, they realize that if they use gold or if they use silver, they can produce different color, and still we have very vivid glasses. And for instance, if they use gold nanoparticles with 100 nanometers and they add it to the molten glass, they can reach orange. Or in the other side, if they use one of the most difficult ones to reach was blue, if they use 40 nanometers nanoparticles, silver nanoparticles, they can produce the blue coloration. Still to date, this still is one of the approaches used to make these kind of glasses, but of course at the moment we know what we are doing, and we know that we can play not only with the size, with the material, but also with the shapes. As I show you in the previous slide, we can have different shapes and we can have different colors because of that. So, but in fact, we can go even back, let's say, to millions and millions of years of evolution. And in fact, we have nature, because nature by itself, it's the most inspiring thing for me, at least as a material scientist, that you have nanostructure or nanostructured features in nature that appear after the billions and millions and millions of years of evolution. For instance, all of us, we saw very beautiful butterflies with very vivid and bright colors. But maybe most of us, we never thought about, okay, why this color, why this feature? But in fact, if you zoom in on the butterfly wings, you can go and see, this is very tricky to see, but you can see that you have very nice and very intricate nanostructures. This is one of the reasons why we have these very bright colors. But why? I put it here, a good example. These very small features, of course, the light will interact differently with these features. So it means that eventually part of the light can be either absorbed if you have pigments, which happens for the case of the birds. These birds, they have very small particles on the wings, so part of the light will be absorbed and other will be reflected. In the case of the butterflies, these nanostructures will scatter the light. So, and the way that they will scatter, it's very precise. That's why you can have very bright colors without having like interference of other colors. For instance, the butterfly was one of the examples with these nano features, and then you have others. For instance, you have a bug, and this case is even more interesting because you have, yes, it's the next slide. We have the assembly of very small layers that can stack with a very precise rotation between layers. And this very precise rotation of the layers will form what we call pitch. And the pitch, depending of the size of it, they will be able to reflect a certain color. Can be, for instance, green, can be blue, but one very interesting feature is they stack and they are rotating while they stack. So means that you have, or the bug can have two colorations, or we can see it with two colorations, but in fact, you have, if you shine the bug with what we call light circular polarized light, all the lights will be absorbed or transmitted to the shell of the bug. While if you have the left circular polarized light, all of that light will be reflected. And this is mostly done or due to the internal configuration of the small crystals that this bug, and this in that case, the blue one, it's a fruit that they have at the shell of it. So this brings me to another concept, which is chirality. Chirality, you have several examples. For instance, the first one, or the most immediate one, is our hands. That you see that your hands are symmetrical, but you are not overimposed. For this, we call chirality. In fact, chirality exists in several examples. Even in our DNA, you have like a left helix, and then you have the right helix. They are symmetrical, they are like a glass reflection, but if you want to overlap them, you cannot. So what this results, it's a way that somehow nature used to store information. Because, for instance, in the case of the bug, you can have the reflection of the light, or you can have it totally absorbed if you are using not the right polarization of the light. And the same, for instance, just to name another example, the same happens in some molecules, that you can have very similar molecules, but the smell that you will get is totally different. For instance, it's the case of spearmint molecule that is, and the other way around, you have caraway. It's a totally different smell. So this chirality, for me, it's amazing. And what we can do, and this picture looks or exemplify exactly what I was meaning, what I meant. You are shining your certain light, and if you have the pitch, which is the difference between, or the distance that you have on your crystals to perform 360 degrees again, so of rotation, you will have what we call the pitch that will interfere or define the coloration that will be reflected. So it's possible to tune this distance between these crystals, and you can have different colorations, for instance, red, blue, and green. For instance, if you have the red ones, means that your crystals will be more apart, while for the blue ones, you have very close stacking of your crystals. And if you put it in a left circular polarized light, you will see very bright colors. But in other, if you put it the right circular polarized light, as I told you, nothing will be reflecting, everything will be transmitted or to the film, to the membrane, and these can be used to, as I said, to store or at least to codify some information. And also for electronics, we used to place these layers of cellulose nanocrystals as a dielectric material, because the cellulose has some properties that can be used as dielectric in field effect transistors, but also due to this interaction, very interesting interaction with the light, we can use it as a filter. So if you have, for instance, a semiconductor sensitive to a certain wavelength, and you can pass the light through the cellulose nanocrystal layers. Depending on the orientation of the light, you can have more or less light shining the semiconductor, so means that you can modulate the response of your device according to the light that is passing through the dielectric layer. And just to show you what I meant with the pitch, so this is half of the pitch, and this is a pitch. So means that we are speaking around 400 nanometers, so means that we are speaking more or less of 500 nanometers of pitch, means that your layer will work or will reflect the light on that wavelength. But still, I gave you one nature-based example of nanotechnology, but in fact, nature still is full of very nice nano features and nanostructures. One of them, for me, is very, very interesting, is the chameleon. As you know, chameleon can change its colors, and actually it was quite recently that the researchers find out how this happens. And the chameleon has very small crystals on the skin that can be very close to each other, and in this case, if they are very close, they will reflect the green light. But when the chameleon gets stressed, he can separate more these crystals, and of course, if the crystals are more apart, they can the light will interact differently with those crystals. So instead of seeing the green light or the green color of the chameleon, we start to see the yellow light. So in somehow, chameleon can code himself or itself accordingly to the stimuli that he gets from the environment, or even in this case from this paper, I guess they put in front of him another male chameleon, yeah, and he was very stressed, so he changed the color, and of course looks bigger actually due to the yellow color. And of course we have other nano features that in fact we find in the nature, the hydrophobicity and the mosquito eyes, the insect wings and shark skins. But in fact these are everything nature invented, let's say, features, but in fact the human is taking profit of it. In the case of the rice leaf, which is very hydrophobic, all of us, we have a very thin layer on our cars or some glasses that can spread, or the water can easily being separated or clean out, because we have very small particles on top of it that avoid that the water start to accumulate. So we have hydrophobic surface. And then the mosquito eyes, it's very important because they have a characteristics of being anti-reflective. So still we have a lot of examples of commercial products with these characteristics. And finally the shark skin. I don't know if you remember, but a few years ago at Olympiad, some athletes used shark skins to swim because of this, because you have like a very a textile with very small nanotech or nano features, let's say, that the friction of the skin or with the water was lower, so they can swim faster, and was not. I think today it's not possible to have this kind of equipment. Okay, I just present you. Okay, it's not working. Just present you the nanotech in nature. Okay, no sound. But most of us, we think about nanotech as something like this. And I don't know if you saw this movie, but by the end, he said, do you like it? It's nanotech. So sometimes, or most of the times, the appealing side of nanotech is this. We think about exox materials with very high mechanical properties, everything very high tech. But in fact, nanotechnology can be from very standard and daily life applications, for instance, sunscreens, cosmetics, but actually we can go even further for not yet these kind of applications, okay, but for very high-end applications. So just to take a few steps back, new scale, new properties, new applications, of course. But what, as a scientist, as a researcher, need to keep in mind to think about nanotechnologies and nanomaterials? Of course, that you have a material, but it's a different scale. For sure, the mechanical and thermal properties will be different. So, for instance, all of us, we heard about graphene and carbon nanotubes. Are very, very interesting. And if you mix it with concrete or with some polymers, we'll have very high materials or composites with very good mechanical properties, which is very interesting. So means that we have to think about these characteristics, but then, of course, we have the physics of it. So we have what we call the quantum confinement, and we saw previously with the case of the butterfly wings that the interaction, optical interaction, will be totally different. So this opens new possibilities for optoelectronics, electronics, and optics. And finally, the chemistry part, or the contribution, chemistry contribution, since we are speaking in a very small scale, instead having, like, imagine if you have a small tennis ball and you start to chop it to very small pieces, the surface area will be increased. So means that if you have more area exposed to a certain element, means that you will have more reactivity. So especially for the sensors, nanotechnology is a great breakthrough. I don't have here any examples of it, but in fact, we can have nowadays sensors with very high sensitivity due to the use of nanostructure. For instance, nanowires, which are very small wires. Of course, it's nanowires. So it means that you can have a lot of those wires in the same space. So it means that the area to react, to be exposed, for instance, for organic volatile element or acetone, or even for detection of some diseases, will be much higher than if you have a bulk or big piece of this material. So the question is, why only now? I start saying that the tools and the processing was a big part of the problem. But as also I mentioned, only by the 80s we start to have the tools that could help us to manipulate and produce materials and devices at nanoscale. But also one very important thing, that maybe only for the last 20 years we start to have like interdisciplinary help or synergies to work on nanotechnology. And just a curiosity, because most of us, we think and we want nanotech, nanoparticles, nanomaterials, but maybe not all of us, we know how to reach them. Actually, there is two ways. You can make a bottom-up synthesis. That's, you start with the atoms, and then you can make molecules, and then make the clusters that will then use to produce your material, your device, or you can go the other way around, top down. As I told you before, we have a bulk, and then you start to chop. Chop, it's not the scientific word, but you can grind it, or you can use other techniques to make it smaller into the nanoparticle size. And then, after you reach that the desired size, you can make your devices. And after we get all the materials with the right properties, because as I gave the example of the gold nanoparticles, depending on the size will depend the color. So after you tune the characteristics of your material, you can have different applications, and I just put it some of them, but there are quite a few. Maybe the most evident one, and it is really pushing the field, it's medicine. You can have, imagine, a cancer cell, and then you can have very small magnetic particles that can eat the cancer cell, and by hyperthermia can kill those cells. It's just an example. I know that a lot of people are working currently on this, but then you can have, of course, when bridging for the talk that Luis gave, you have the electronics. You can make very small devices that will pave the way to a different world of electronics. And then you can have the textiles, which is now pushing also a lot on this. For instance, you can have clothes with silver nanoparticles, which are antimicrobial. So it means that you can have like nearly a self-cleaning shirt. And of course, we have energy, robotics, and so on, just to name a few. So maybe the most interesting part here is the application to IT, but all the time it's not a problem, it's a challenge. At the nanoscale, the most fundamental properties of the materials and machines depend on their size in a way that we don't know any other scale. So means that at the nanoscale, more than the macro scale, everything is way more challenged, and the nano, I don't want to say nano power because the rules are imposed in a different way. And for that, in fact, it's a very huge challenge to define or to build new devices. But of course, with a big challenge, most of the time comes a big breakthrough. So it's expected with this nanotechnology, we can have smaller, faster, and more efficient. So it means that eventually with the same amount or the same size, you can have a lot or much more devices that we get at the moment. And just to make a bridge again with the last one, we spoke, or Luis spoke about the transistors and how these empowered the transition to the digital world. But in fact, we can go and see, or at least speak again, about how really nano empowered a lot of things. So in the 47 from the last century, a transistor, a single one, had 2 centimeters, just one. In 71, the first processor, Intel, has 2.3 thousand transistors with a size of 10 microns. 50, no, it's not 50, that one is 50. In 2002, we had in Pentium 4 50 million transistors with 130 nanometers. And 50 years after, Intel again showed that they can do nearly 3 billion transistors with 10 nanometers. And this is already, it's not updated because by sure that this year they are very close, not yet there, but very close to reach 1 trillion transistors in a single device. So all of this, of course, it's powered by nanotechnology, because, of course, that I think, or this is my personal opinion, the problem is not the material at the moment. The problem is how you properly manipulate and make this kind of the device. Because when you think 10 nanometers, you saw 10 nanometers was 1,000 times smaller than a red blood cell. So means that the challenge to reach this scale, it's so high at the moment, but at the same time opens let's wonder what came next, because this is already way, or at least for me, way above or far beyond that what I was thinking about. So what came next? I think, personal idea, I think that device with high speed, short range communication, very power efficient computing, high density memories and logic, and of course quantum computing, that Carolina will speak about next week. So I hope I gave you a glance of the opportunities that nanotechnology, or at least nanotechnology with a bit of nature on it, and I'm hoping for questions. Thank you.
Okay, we can start with the questions. Anybody? Not yet. Okay, so I will ignite it again. So I do have a question. You showed us this biomimetization and the way that nature can actually codify. So could we have alternatives to the limitations we have nowadays regarding materials, regarding semiconductors, right in front of us in nature? Like, could we have alternatives there that we should look into?
I have to say that I'm biased, so yes, totally. In my opinion, nature, and I gave you some examples, knows way better than us how to store information, how to keep things in a very small and very tidy way to make new materials, or at least gave us some ideas to produce new materials with new properties. Because the example that I gave for the cellulose, in fact, cellulose is something that everyone has. We have a piece of paper, it's cellulose fibers. And mechanically, these fibers are not very robust. But then you start to go downsize it, you can finish with cellulose nanocrystals. And these cellulose nanocrystals by itself, the properties or the mechanical properties are totally different. So it means that at that scale, the materials, or we can have a brave new world of applications at this scale. So of course, that for me, biased again, we have a lot to learn about it, with it.
With such a small scale, what are the standards for building up microchips and microtechnology? Like, do you have to deal with, like, even light behaves differently inside of nanoscales? So what is a factory for nanochips? What is the standards? It has to be vacuum, it has to, how do you do that?
All the chips, regardless of the size, they are making or made, most of them in vacuum chambers. But of course, when you go to this level of miniaturization, besides the chambers that you need to reach very high vacuum, because you need to precise place like atoms. In this case, I guess I have, okay. In this case, you have like, just like a few atoms close to each other. So it means that you need to have very high vacuum, very good equipment, but besides that, you have another problem, which is the clean room where it's produced. So in this scale, eventually you don't have humans handling this kind of devices. You have robots that take the wafer and from one chamber to the other. Otherwise, you have even the people that eventually go and to operate some machines. You cannot move very fast, otherwise you will increase the number of particles on the clean room. So everything needs to be very, very controlled. So everything is much more challenged, and that's why I put it there. Cheaper to manufacture. Not sure about it.
Yeah, we have a question from a student who's watching via streaming, and he's the student that started the hardware club here in Lisbon, Eduardo. So thank you, Eduardo, for asking it. So considering that the last iPhone has that the processor of the last iPhone has 3 nanometer transistors. What nowadays is the smallest size possible in theory for transistors? I hope I got it right.
Today, when I was just checking from some details about the size and the number of transistors, I found that Intel is planning, or at least they are willing, to release 2 nanometer transistor in 2024. So I guess the limit is there, but I think what is the limit at the moment, we don't know. But I guess it was last week, we saw a trend of the processors, and Intel is already planning to go to angstrom. So it means that we are even go one size smaller, let's say, to the scale that we are speaking about. So everything 2 nanometers for me, it's already way. It's not blue sky, but I think it's possible. Maybe go further than that can be tricky.
Yeah, to add on this one, last week we saw a trend on the evolution of the transistors. So the streaming is still live on YouTube. So please go check it, because I think part of the answer is there. We also talked about a single electron transistors, which is even crazier because it would be literally the whole working function of a transistor would be handled by one electron. We're not talking about one atom, we're talking about one electron. So this is already bending all the physics rules, right? And I mean, we have a trend where we're already bending some of the rules, definitely. So in the future, we will bend even more. And more questions from the round? Questions? No? Okay. Yeah? Okay. Okay. We were we were not sure.
Several years ago, I read an article about nano robots and also nano factories. And in the article, they were actually saying that they would have nano robots that would clean the dishes on a molecular level. I wonder if you can, where are we when it comes with nano robots, and what kind of research is being done now?
Of course, that is the appealing side of or one of the appealing sides of this nanotechnology. The nanorobots to clean the dishes will be great, but the effort actually, it's, from what I have been observing, it's making towards nanomedicine. Because with the nanomedicine, they were expecting that if you have like a nanorobot, maybe the concept of nanorobots is now a bit outdated, but the idea of have a drug release, controlled drug release, or nanorobots that will release the drug on your body in the precise cell, it's something that is being pursued, but the problem, or from what I have been seeing, this raises a lot of ethical issues, because you are putting something very small, because when you think about nano, it's something that's smaller than our molecular or the cell walls, so means that eventually you are trying to make it right, but the problems that you will get with that, we don't know. So it's something that eventually, if it's being made, it's not well stated and clearly disclosed to the community because of these issues, and you have always to address nanotoxicity and so on that needs to because of course we have sometimes the problem, okay, you are using sunscreen with nanoparticles, but now they are saying that only that nanoparticles eventually can have they can remain in your body for a long time. So it's a very interesting field, but still it's uncharted water, so we don't know yet.
More questions from the round?
Yeah, cool. So my question is a little related to that. So you said specifically that our definition of a nanorobot, it's outdated. Okay, so how big is can we expect to get there? Is it let's say remote controlled molecular atom considered a robot? So exactly how small can we expect it to get, or how big?
The idea of nanorobots is more related with what you said. With having atoms working as tiny machines, okay. So having not a robot like the way that we think about in the movies, but having machines made of molecules that can move and address or reach a certain place. And I saw that some trends and some ideas of having like a protein that could move, and I don't have on top of my head the number of atoms that they were, but I don't want to lie, but I think it was something like 8 to 10 atoms to make it move. Yes, very, very small.
It's not a question, it's to add a little bit to that, and also there was a question about the robots, the nanorobots that could clean our plates. I think nowadays we already have that. We have detergents, right? They were invented by us. They are molecules, and we could consider them already like nanorobots helping us clean our plates and so on, right? So I think it's really a matter of how you define what a nanorobot is, right? If it's a molecule, if it's an atom, if it's something bigger like that one over there, or if it's already something micro. I mean, there's so many levels, and that's why this field is so huge and so interesting, because there's so many points of views and so many things to think about. So, yeah.
Yeah, I'm gonna add on that too. I remember this hyperthermia work we did in college, and we were using silver nanoparticles to create this heated camp around tumor cells, and targeting only this area to blow up the cancer, basically to blow up the cancer cells. So you know that our cells above 40 degrees, so the proteins start to degrade, and they eventually will enter apoptose, which is suicide of the cell. So what we were trying to do is to drive these nanoparticles, these silver nanoparticles, to be around the tumor and very locally increase the temperature and promote this suicide of the cancer cells. And basically, in this case, the silver nanoparticle, which is just literally a ball of silver, was guided by magnetic fields into like this area that we wanted to target. And in this case, it was just the silver nanoparticles that were the robots. So again, when we think about, and the problem also is a little bit because of Marvel, you know, when we think about robots or nanorobots, we literally imagine tiny robots. And we have to debunk that idea, because the robots will not look like the chips and the ones that we have in the robotics room, you know. They will look like that. They will look in a very weird way, and they can be just like a gold nanoparticle or silver nanoparticle, and that somehow we can teach them to go to the place that we want to be. Regarding the biomedicine, we need to enter a whole concept of this connection, this connectivity, which is biocompatibility and whatever, which is the connection between the particles and the body that we want to target and so on. And we will not go into that because we're also more interested on the IT area. But I think that we have to deconstruct a little bit what Disney put in our minds when we talk about nanorobots. So yeah, that's pretty much it.
Something on this? Yeah, just to add something on this, what Carolina said, it's very important, because eventually we think robots that can move and go to a precise place that we program them to go. But in fact, with magnetic fields, we can move some particles. Okay, if you swallow some nanoparticles, they will make the move through your body. But if you want to put it in a certain place, then you have to have external stimuli to put it in the right way. So it's wave-guided robots, let's say. Exactly.
So usually when we hear about nanotech, especially in our department, we hear about transistors and so on. But where else might we find nanotechnology in computers nowadays? So where can we expect to get breakthroughs or big breakthroughs besides the computer modules, the CPU, RAM, I'm missing one, GPU.
Okay, maybe this is not the expected answer, but of course, what you mapped all of the nanotechnology niche, let's say. But for cell phones, you have the displays, or where you also have a lot of nanotech there. You have quantum dots that start to appear as a good thing for very vivid and bright displays of the cell phones, or the cell phones not yet, but for the TVs and so on. So in fact, it's all over. So it's surrounding us. From the very high-tech as computer engineer and science, but also, as I told, to very, and as Paul said, to the small pot that you put on your dishwasher machine, or in for the deodorant, or the sun shield that you use. So it's something that we cannot deny anymore.
Yeah, just a quick note on that. If they try to sell you a quantum TV, don't buy it. Yeah, at least for now. But OLEDs, for example, the OLED is also nanotech, so behind it, yeah.
Maybe because of my training, I always think about nanotech in something with inorganic materials, but it's a way wide applications with nanotech using organic molecules. And OLEDs, AlmaScience that we have on our cell phones and so on, everything relies on nanotech. Because in that case, you have several layers of nanotech, that you have the transistors, and then you have the filters, and then you have the polymeric layer that will be emit the light. Of course, you have nanotech behind that.
More questions?
I don't know how to word this, but what is in the future? What kind of technology that will come from nanotechnology makes it more exciting? Like,
Yeah. So just to make a disclosure, but it's right. I have two. The quantum computing, because it's something way out of the box and something that I don't know. So immediately it's something that it's the big next thing. But also what I think, and I hope that will not make like a revolution, but will be very important for me, it's biomimetics. So go and see what really works on the nature, learn from it, and to make it in a scale, in a nanoscale, in the way that we can control. In my opinion, it's something that will be very important in the future.
I'm gonna add on that one too, because not next week, but the week after, we're gonna have another colleague here talking about AI and the future of hardware for AI. And I think on that one we will also have a bit of a disclosure of how nanotech can revolutionize this field. So I think if you like neural networks and so on, nanotech is also there. So yeah. More questions? Then I think we can close, because we also started late, so it's already pretty late, guys. So thank you everybody for joining. Carol, you want to join us? So like I said, please join us too. So like I said, next week we're going to have a few more masterclasses. Next week we're going to have one about quantum computing. And then we're going to have artificial intelligence, the future of hardware for artificial intelligence and neural networks and so on. So if you enjoyed this glimpse of what microelectronics is and what nanotechnology is, you're going to really enjoy the next ones that are coming. Then we're going to talk about cybersecurity and how cybersecurity can handle all these tech revolution, all this tech revolution that is coming their way. And last but not least, the last talk we're going to have is about how to be an entrepreneur within this tech revolution. So please join us, streaming also. So if you enjoy these, you can also reach out to us, to anybody from School 42, and also to us if you have more questions. So